This is the second half of Chapter 12. My name is Pete Waller, Center Pivot Irrigation Systems. So the center pivot irrigation spatial model can place pivots in a field based on latitude and longitude of the center of each pivot and the number of spans and angular sections, a number of pixels on the worksheet, and so on. And you can specify the elevations of each of the spans. So the way you do it is in the CP parameterization page. And so you write down the center pivot information right here. And then you just put create pivot field, and it duplicates the information here. Here's the center latitude and center longitude for each of the pivots, and here's each of the pivot lengths. 400 is the number of pixels on the worksheet covered by the field, so if you want the pivots to appear bigger on the spatial data page, you just make it cover more pixels in Excel. And then you just push create pivot map, and it'll do so. And you can also say keep elevations and just put true there in that cell, and what that does is save the elevations you had in there previously. If you don't, it'll just overwrite them, and then you won't have the elevations. And then the center pivot spatial data page, the output will be like this. It'll show the, it'll index, so for instance, here's pivot 1, here's the 4 angles in pivot 1, which were specified, and here's the 4 spans in pivot 1, or in each angle. And so it'll go out 1, 2, 3, 4 in each angular section, and then it has the center, latitude, and longitude of each of the spans, or the spans and angles, and then it gives the elevation of the center of each of those. And then you can delete all the pivots if you want to, but anyway, they show up to the right of what we were just looking at, and the radial numbers are radial sections are numbered 1, 2, 3, 4, and then it goes to the next arc, and then the next arc, and then the next arc, then it goes to the next pivot, and so on. So we specified we were putting 3 pivots out there. 2 had 400 meter diameter, each had 4 spans and 4 angles, and then this had 300 meter length pivot. And if you press delete field, it'll just erase them all. And you can specify hundreds of cells with the program. Okay, let's move on. We'll use that in just a little bit, but for right now we need to discuss some of the basics of pipe hydraulics. And so we'll first look at sprinkler spacing. So sprinklers are spaced along the pivot at varying distances. Usually they're closer together the farther out you get. These are the drop tube sprayers that are used in Arizona. So to avoid evaporation, rather than having large sprinklers on top, they have closely spaced sprayers down low. And so the water doesn't have so far to travel to get to the ground. And so the sprinkler flow rate is calculated according to the this equation, where this sprinkler at distance r from the center has spacing r between sprinklers at that locations. It's this radius distance from the center of the pivot. This is the flow rate of the entire pivot, and then this should be divided by, so it's r max squared. R max is the total length of the pivot. So for example, if we have a sprinkler spacing of 1.5 meters, and we're looking at a sprinkler 400 meters from the center of the pivot, and the 400 meter pivot has a 95.3 liters per second flow rate, then the flow rate of that sprinkler will be 400 meters, the distance, times the spacing, times 2, times the flow rate of the entire pivot, divided by 400, the length of the entire pivot, or 0.71 meters per second. And so the units work out, even though they don't agree. Okay, and if we looked at a flow rate of a sprinkler that's only 200 meters from the pivot point, then it would have, again, 1.5 meter spacing, but the R is 200, that's the only difference, and so it'd have 0.36 liters per second flow rate. So the flow rate at 200 is half the flow rate at 400. And the reason for that is the area is based on the circumference and the distance between sprinklers. So the distance between sprinklers is the same, and the circumference is a linearly related with the distance r. Remember that circumference is 2 pi r. That's why they're half, not like squared as you'd expect with areas. So here's a sprinkler that we looked at in Queen Creek area, Arizona. And here are these individual sprinkler flow rates. And you can see that the flow rates go up as you get further and further from the pivot point. And the reason that they go up is because they're covering more and more area. And as we calculated, the Q is greater. And the way that this pivot company set up this sprinkler is that they had 5-meter intervals close to the pivot point. Here's the pivot point, distance from the pivot point. And here's the whether flow rate or interval or application rate. But the distance is 5 meters between sprinklers, or 5 meters between sprinklers, and then 3 meters between sprinklers, and then 2 meters between sprinklers farther out. They put them close together for a higher application rate. So you can see that for the 5-meter interval, they keep using larger and larger nozzles, and so they're getting a relatively uniform application rate. This line is the application rate. So you can see that even though the pivot's traveling faster, farther out from the pivot point, because it's using larger and larger nozzles, the application rate stays the same. These difficulties are generally focused on the wheel area, so they don't tend to spray into the place where the wheel is going, because that will cause the wheel sometimes to develop a rut if it's going across wet soil. So they have sprinklers spraying either way. So that's probably a wheel. Here's probably another wheel, a wheel, a wheel, a wheel, a wheel. And then these are variable because they're close to the pivot point, and there's it's very difficult to control the application rate when you have such a large change in area with distance. Out here, the change in the amount watered is much smaller, and so they can control it. So they have this gradient of pivot nozzle diameters as they go out, and then they switch to 3-meter interval, and they start over at a lower diameter, and then they go out again. And you can count the number of nozzle diameters just by counting the number of flow rates. So I think there's like 22 or 23. Then they start over at this diameter here and go up, and then they start over at this diameter here and go up. And so pivot manufacturers have computer programs to determine the optimal sprinkler flow rates and nozzle sizes with versus distance from the pivot point. So the farmers receive a ring of nozzles from the manufacturer and remove the nozzles one at a time and put them on the sprinklers whenever they need to replace their nozzles. So I already answered this question: how many different nozzle diameters are included in the nozzle package? Well, you'd count up, and this is 22 different flow rates. One of the rules of thumb in irrigation is that you should only have 20% pressure variation between sprinklers. For example, if one sprinkler operated at 25 meters pressure, you wouldn't want another operating at less than 20 meters pressure. And the reason for that is the orifice equation. If you have 20% variation in pressure, you only have 10% variation in flow, because this is square root. And for example, if you had 2 sprinklers with the same nozzle size, and one operated at 20 and one operated at 25 meters pressure, then Q2 would be 0.91 of Q1, or just 9% pressure variation. With a center pivot, I think you probably want to aim for a higher uniformity than just having 10% variation, because you can control the nozzle sizes so well. But sometimes you have variation in elevation, and so you're going to have higher flow, and the center pivot is in a higher part of the field than in a lower part of the field, or vice versa, actually. So often center pivot manufacturers will install pressure regulators along the pipeline so that no matter what the pressure is in the pipe, all the sprinklers will get the same amount of pressure. For instance, this is a 30 psi pressure regulator. And this would be installed upside down. It'd be screwed onto the pipe, the drop tube, and then the sprinkler would be screwed onto it. There's an equation that can be used to calculate sprinkler nozzle flow rate based on the diameter. and the head, or the pressure, and the sprinkler nozzle discharge coefficient. And so this is the equation for American units, PSI in gallons per minute. And so if we had or we can also convert that using dimensional analysis to metric units. And so this is the metric unit equation, where Q is in liters per minute, diameter is in millimeters. So here's an example. What is the flow rate of a 3.57 millimeter nozzle? That's a 9/64 inch diameter nozzle. Those are very common. At a pressure of 50 psi, which is a normal pressure that they operate at, and that's the same as 340 kPa. So Q would equal 0.066 times 3.57, the diameter squared, times the pressure to the square root, times 0.97, which equals 15.2 liters per minute, or 4 gallons per minute. And so the center pivot program will calculate all the flow rates for you going out the pivot. And you can just put in the nozzle coefficient, and it'll actually calculate I think it'll calculate the correct diameters. I forget right now. But anyway, it makes the calculations for you as far as flow rate, and then it will calculate the distribution of flows over the center pivot. Normally the center pivot manufacturer might give you that information, but this program does that also. So in order to do the economic analysis, you also need to put in some other information, such as the height of the pipe above the ground, the sprinkler height above the ground, because if it's 1 meter above the ground, you have to add a meter to the pressure requirement. And then this also, you can specify the pressure loss from the pump to the pivot inlet, and also elevation gain. And then there are 4 sprinkler spacing intervals, so you put those in, and after 8 meters from, or up to 8 meters, after 8 meters from the pivot, they're 4 meters apart. After 50, they're 5 meters apart. After 200, they're 3 meters apart. And after 325, they're 2 meters apart. There are also pipe intervals, and so from 0 to 320, the diameter is 248. From 320 to 380, it's 198. 380 to 400, it's 163. And so this is the cost per meter. So this would enable you to calculate costs of the pivot. So there's certain design objectives for pipe diameter calculation. One is to minimize cost, and the minimum capital cost will be with the minimum pipe size, obviously, and also if you didn't have so many components like regulators. Then you would minimize the energy cost by increasing the pipe size, because then you wouldn't need as much pressure to push the water through the pipe. So those are competing objectives. So that's why you need to use energy and pipe hydraulics analysis in order to make the decision. Also, you would want to minimize the water cost, which would be done by increasing the uniformity, which either means pressure regulators or larger pipe, because you'd have more uniform pressure, or better designed nozzle packages. And also you'd want to minimize the water application depth and evaporation. And in general, you want to maximize yield and minimize cost. Well, the pipe calculation with a center pivot can be made much easier by just calculating the flow rate through the entire pivot and then just multiplying by a factor, rather than calculating flow rate from sprinkler to sprinkler. You can just assume that the flow is going through the entire pivot and then multiply by a factor. So for example, if we had a pivot with a flow rate of 50.3 liters per second and a pipe diameter of 19.79 centimeters and a length of 380 meters, we could calculate the pressure drop. And so we just this is a constant. This is the 380 meters. Here's the flow rate Q, 50.3. This is Hazen-Williams C coefficient, which for center pivot pipes, it expresses the roughness is about 130, at least new ones. And then the diameter is 198 millimeters, or 19.79 centimeters, but in this equation it's millimeters. So that if the flow of the pipe was going through the entire pipe and no nozzles, sprinklers were on it, the pressure loss would be 5.24. But we can multiply by the Christensen's factor, 0.54, the entire friction loss, and this is the friction loss for water going through a pipe with multiple outlets, 2.8 meters, which isn't too bad as far as pressure loss. So with center pivots, you want to minimize pipe diameter, and part of the reason is the structure has to hold the steel pipe with water high above the ground, so there's extra cost there. But reducing pipe size increases pressure loss, and with a pivot especially, you wouldn't want to have too much pressure loss because you're paying for it just in that one pipe, so you want to minimize your pressure loss. So with pivots, it's especially important to do the hydraulic analysis. You can also calculate the pressure loss section by section, which is what the computer program does in the center pivot irrigation program. You calculate the flow in each pipe section, so you set up Hazen-Williams equation, which I just showed you for the entire pivot flow rate, but you can set it up for each pipe section and add up the pressure losses. And so that's what this graph is based on. Here's the inside diameter of the pipe versus distance from the pivot. Here's the pressure loss, and here's the flow rate. So the flow rate goes down as you go farther from the pivot point because it's going out the sprinklers. Okay, let's make a decision, or let's look at a question that's often asked is, should pressure regulators be used? Well, you'd think so, but the problem is they cost money, and also you have to pay for 3.5 meters of extra pressure in the center pivot. So let's look at a question, a practical question. We have 1,200 millimeters of water required during the season for the crop. The 400 meter pivot covers a 50 hectare area. The water application efficiency is 85%. The pump energy efficiency is 85%. The cost of energy is 10 cents per kilowatt hour. We'll assume a 20-year project life and a 6% required rate of return. So the depth of water required, if there's 85% irrigation efficiency, we take the crop water requirement and divide by 0.85, or 1412 millimeters. The increased pressure requirement is 5 psi due to pressure regulators, 3.5 meters. So let's calculate the extra energy per hectare needed with this equation that's from Chapter 2, which I loaded into the content section of D2L. So there's 3.5 meters extra pressure. The total depth of water required is 1411 millimeters. The coefficient is 0.0272. The pump efficiency is 85%, so there's 158 kilowatt hours per hectare required. And then if you wanted to calculate the energy cost per year, then if we had 158 kilowatt hours per hectare times 10 cents per kilowatt hour times 50 hectares, it'd be $790 extra energy per year. And if we convert to the present value for a 20-year project, 6% rate of return, that'd be $9,000 extra dollars just in energy for using pressure regulators. So when do we use pressure regulators? Here's the design pressure, and let's say the design pressure is 20 psi, and our elevation change is 7 psi. Well, actually 7 feet. So this line is kind of hard to explain here, but this line means if you had more than 20% elevation change of your design pressure, then you would use pressure regulators. So if you had 15 feet elevation change and your design pressure was 20 psi, then you would use regulators. But if you only had 5 feet of elevation change, that wouldn't result in that much pressure variation, so you would not use pressure regulators. So that's, I was trying to explain that graph, and this is the in-class exercise. It's easier if you just write down like 10 through 50 meters and then elevation change in meters using the same units, and you can see that at 4 meters elevation change and 20 meters pressure, that would be where the line would go. So it would go up like that. Okay, now we're going to look at how to do the pipe calculations. So we'll be doing it for center pivot number 1. And in center pivot number 1, the elevation for the first 4 spans in angle number 1 is 100. So it's level going out this way. But for the second 4 spans in angle number 2, it goes 101, 103, 105, 107. And for the third set of 3 spans, or 4 spans in angle number 3, the elevation is basically level, 100, 100, 100, but it goes up a little bit at the end. And then it goes down in angle number 4, 99, 97, 95, 93. So basically it's level in this direction, up in this direction, down in that direction. So we can go back to the CP parameterization page, and we can click the Center Pivot Seasonal Simulation button, and now we can go to the CP Flow Output page, and this calculates all of the center pivot flow rates and so on. And so here's the sprinkler numbers. You can see that the slope changes, sprinkler number versus distance, and the reason for that is they're more widely spaced at the beginning, and then they become closer and closer together. And then these are the sprinkler liters per minute flow rate based on their distance from the pivot. And this is the diameter of the pipe, and this should actually be up here. This is a mistake, but it decreases towards the end. And then this is the liters per second in the pipe as you go out. These are the elevations of each of the arcs. Remember I said that the first arc, it was level, and then in arc 2 it goes uphill. Arc 3 it was level to a point and then it went up. In arc 4 it goes downhill. And then these are the pressures in the sprinklers, and you can see that the pressure goes down most for the uphill arc, arc number 2, and the pressure actually increases at the end of arc number 1, and then the pressure is more even for the middle 2 arcs. These are the flow rates in the different arcs based on the fact that the pressure is higher, so we're not using pressure regulators. And so you can see that the flow rate goes up, and then another spacing is used, which we specified in the CP parameterization page. And then these are the relative application rates. You can see because the pressure goes up and the downhill, the application rate goes up. So if 1 is our required application rate, then we're applying almost 20% more on the downhill phase than we are on the uphill phase. Let's go back and we'll change to using a pressure regulator. So we'll put true here, and we'll click the Center Pivot Seasonal Simulation button, go back out to the flow output, and you can see that the relative application rate is the same all the way across for all the sprinklers. That's the result of using that. But we can look and see that the required pressure at the beginning is 30 to go uphill, or actually it's around 30, and that's to I can't remember exactly why, but anyway it's around 30. But if we go back to CP parameterization page and we type false for the pressure regulator, we run it again, you can see that our required pressure is much less because we don't have the extra 3.5 meters pressure for the pressure regulator. It's 25 instead of near 30. So that's the plus and minus of using a pressure regulator. On this field we'd want to use one because we have 20% variation in flow, but we would have to pay for it by having extra pressure. All right. Let's go to the summary data. And in the summary data, we can see what our total profit is for the different depths of water applied, average depths of water applied during the season. Okay, so in the summary data, we have arc number 1. We have our different possible depths of water we could apply. Arc number 2 for the same depths. And these are just different costs and yield and so on. And so anyway, it totals up all the arcs and it gives you the total profit per hectare. And you can see that your total hot profit per hectare is a maximum here. It was 758 with less water applied and 758 with more water applied, but the maximum is right there at applying 66. And the reason for that is we have our water cost, we have wasted water, we have a relationship between yield and the amount of water applied to different sections of the field. So this enables you to calculate the optimal amount of water to apply during the season. And that is all based on this data down here. And so these are relationships. This is yield versus applied water. This is a relationship for that. And this is the effect of salt and so on. And so you can see that, oh, and this is the rainfall that you'd expect. This is the coefficient of variation. So there's variation between sprinklers. And, you know, it's not a perfect application. So if we go over here to the yield output, you can see that the yield is not constant throughout the field. It depends on how much water is applied to that specific spot. And so what I did was I developed a random number generator and Monte Carlo simulation so that we can have an idea of the yield at each part of the field. And so the computer program goes through and calculates the yield in each part of the field, and then it'll summarize it in the summary data page. And so you can make a decision, well, how much water should I apply to the field? And then you could make a decision based on all your costs of energy and so on, whether you wanted to use pressure regulators or not. So I think in your homework problem you're asked to investigate if you had a variability of, say, a CV of 0.1 instead of 0.2, well, all you do is change this 0 to 0.1 right there. And let's just do a dramatically different one. We'll change it to 0.5. And so we'll go over here to the Center Pivot Seasonal Simulation button, and we'll go back to the summary data page, and you can see that the profit has gone way up. And actually, we would want to apply less water, 603, and we're getting the same amount of yield because we have much more uniform application. If we go to the yield output page, it looks worse. I don't know why. Yeah, I don't know exactly why at the moment. But for your homework, you can just go ahead and use that 0.1 value. And I'll try to do a better job on the lecture, on this lecture when I get back from Phoenix.